Welcome people of the pre-seminar. So this week's speaker is Jakub Knesel, who is a PhD student here in Prague, and he is going to give us an overview of the homological perturbation lemma. Please.
Thank you for the introduction. I'm thankful for the opportunity to give a talk at the pre-seminar. I will talk about the homological perturbation lemma. So, yeah, great. So first we will give definitions of the objects appearing in the homological perturbation lemma, and also we will introduce some basic constructions. Then we will also mention some example of
Yes, starting the video.
to start my video.
Yeah.
Okay. So first, in the definitions, we will define a homotopy retract. We will then give an example, which will be mostly inspired by the Hatcher's algebraic topology book. After that, we will state the homological perturbation lemma itself. And then we will also include an example of its application. So my slides follow mostly the paper of Marvin and his co-authors. So this paper, Global Homotopies for Differential Hochschild Cohomologies, the appendix. Also, I will also reference the paper by Marius Kreinik, and for the examples, I will reference the books Algebraic Topology by Alan Hatcher and Bott and two differential forms in algebraic topology. So we start by defining a homotopy retract. So throughout these slides, R is a commutative ring, and the homotopy retract is a triple IPH, where so we have two cochain complexes of R modules. I and P are maps between these cochain complexes, and H is a homotopy between the identity and the composition IP on the chain complex D. So in this picture, this is just a schematic picture of how the homotopy works. So basically, if we go from Dn to Dn by the map identity minus IP, it's like going this way and this way and adding the two results together. And we will also graphically depict the data IPH like this. Yeah. So I always imagine this I being some sort of inclusion and the P some sort of rejection. This will also be the case in the examples we will introduce. So some special cases of homotopy retracts are deformation retracts, which are homotopy retracts with the additional property that the composition Pi. So this is the identity on the chain complex C. And even more special, so we call that a special deformation retract, and that is a deformation retract which also satisfies these three properties. So in particular, the map P vanishes on the image of H, and H vanishes on the image of the map I. Okay, so homotopy retracts admit many like basic operations. Given two homotopy retracts, so here we can obtain the composition homotopy retract, where the maps I and P are obtained as a compositions of the maps I and P from the two homotopy retracts we start with, and the homotopy on the resulting homotopy retracts is constructed like this. So composition of homotopy retracts is associative. I think this is easy to see for the maps I and P. If I had a third one, I would just post-compose here with I3 and pre-compose here with P3. And so the only thing to check is that it is also associative when constructing the homotopies, but that's just an easy algebraic manipulation. And also composition of deformation retracts and special deformation retracts yields another deformation or special deformation retract. And this is very easy to see for the deformation retracts, because if these maps compose to the identity on D and these two maps compose to the identity on C, then certainly these two maps also compose to the identity on C. And then one also has to, in the case of special deformation retracts, one has to check for the homotopies. There is also a notion of morphism between homotopy retracts. So given two homotopy retracts, so the rows of this diagram, morphism is a map which, after a long contemplation, I decided to name phi. Is a map which commutes with the two homotopies. And then it actually induces a map between the chain complexes C and C prime, just by going this way, then applying phi, and then going this way. Okay, we can also take direct sums and tensor products of homotopy retracts. So direct sum is just a pointwise addition for both maps and the homotopies. And for tensor products, we have these formulas. So the two maps are just tensor products of the maps we start with, and the homotopy H prime for the tensor product is defined by this formula. And once again, direct sums of deformation retracts are deformation retracts, and if we start with special deformation retracts, we obtain special deformation retracts. And this is also, like, in both cases, both for direct sums and tensor products, this is easy to see from these formulas. Okay, now we can give an example of a deformation retract. So this is from algebraic topology. It is one way how to define and prove the existence of the Meyer-Vietoris long exact sequence in homology. So given a topological space and its open cover consisting of two open subsets U and V, we can first consider the chain complex D, which is the singular chain complex. So D minus n is the free abelian group of the on the maps of this form, so continuous maps from the n simplex into our topological space X. And the differential is just the boundary operator. Okay, so which assigns to a map of this form the alternating sum of restrictions to its faces, which are n-1 simplices. Okay, so that's the chain complex D, and the chain complex C will be this subcomplex, which is the free abelian group on the singular simplices whose images are contained in one of the two open subsets U and V. So there is a canonical inclusion of this free abelian group inside this one. And then in the other direction for the map P, so if we have a continuous map from a n simplex to X, we can divide using iterated barycentric subdivision. We can divide the simplex into smaller ones until the restriction, so into these smaller n simplices. And we can do that until eventually the map sigma restricted to each of these smaller simplices. So the image of these restrictions are contained inside one of the two open subsets. And then we assign to sigma the sum of the restrictions to these smaller n simplices with some plus or minus ones. The details are described in the book of Allen Hatcher. So I think this is a good picture to illustrate how the map P works. So if I start with this large 2 simplex, it is not contained in either U or V. But if I subdivide it into these smaller 2 simplices, then so these 2 are contained inside U, and the remaining 4 are contained inside V. So to this 2 simplex, which is in the chain complex D, or in the singular chain complex, we assign the alternating sum of these small six to simplices. Okay, so it is easy to see that if I go this way and then this way, then if I start with a simplex which is contained in either U or V, then I don't need to subdivide it into smaller pieces in order for me to land back in here. So this map post-composed with this map is the identity on this cochain complex. And then in Hatcher, there is a very technical construction of the homotopy between the identity on this singular chain complex and the composition IP. And so this is then a deformation retract. And actually this construction can be done for arbitrary open cover U of X. It doesn't need to consist of only two open subsets. But when it does, we can use it to construct the Mayer-Vietoris long exact sequence in homology. So there is this short exact sequence of chain complexes, so the singular chain complex of the intersection, then the direct sum of the chain complexes of the open subsets U and V. And so if I take a simplex here, I assign to it the pair. So if I start with sigma here, I map it to sigma plus sigma. And then from here, I take the difference between the two factors. This is a short exact sequence. And because this one is quasi-isomorphic to this one, to this chain complex, I can I can write the actual homologies of this chain complex in this induced long exact sequence. Okay, now we move on to perturbations. So if we start with a homotopy retract, IPH, perturbation is a map B which goes in the same direction as the differential on D, and it has to satisfy that if we perturb the differential on D by this map B, it is still a differential. Some special cases of perturbations. We will be mostly interested in the case when the perturbation is small, and that means that the identity plus this composition, so the homotopy followed by the perturbation, is an invertible map, and perturbation is locally nilpotent if for any x, if I apply this composition enough times, I get zero. So locally nilpotent perturbations are special cases of small perturbations. So here is a specific or explicit formula for the inverse of this map in such case. So in Kranik's paper, there is this lemma that if I have a small perturbation, then this means that this map is invertible. But what if I also consider identity plus decomposition in the other order, so HB? Then this is then also invertible map, and so this lemma states the explicit formulas for the inverses. This is the proof of this lemma consists only of algebraic manipulations with and usage of the properties of the involved maps. And this lemma we needed before because here we, when defining the perturbed data, we are using both of the composition BH and HB, and we are inverting them. But so if we have a homotopy retract, IPH, then we define the perturbed data like this. So we have capital P, capital I, and capital H. These are the formulas for them. And the homological perturbation lemma states that the perturbed triple, capital I, capital P, and capital H are still a homotopy retract. And in the special case when IPH is a special deformation retract and the perturbation is locally nilpotent, then the perturbed homotopy retract is also a special deformation retract. Okay. Can I move on, or do you maybe want to like write down these formulas or look at them a bit more?
Some questions on these formulas, or seems to be fine. So
Okay. Okay, and so the most important corollary, which I think Marvin will also then use in his talk, is the corollary about the double complex. So if we have a double cochain complex with, so this partial is the horizontal differential and delta is the vertical differential. We also denote by dm this total cochain complex and this is the total differential. So this is where I wanted to draw this picture. So these are the modules in my double complex. I have the differentials going in like this. So these are the vertical differentials, delta. And these are the horizontal differentials denoted partial. Then, so then if I take the direct sum of this row, this is then the element of the total cochain complex. And then the differentials go this way. Okay. And then if we take a collection of some R modules, each regarded as a cochain complex centered in degree 0, and 0 in the other degrees, we have the following theorem. So if for each k there is a special or there is a deformation or special deformation retract from this like a cochain complex concentrated in degree 0 into the kth row. So we have deformation retracts for each row. And some homotopies. Then there is also an induced differential on the chain complex C, which is just the collection of these modules. So this way. Okay. Yeah. So in this case, we then have a special deformation or special deformation retract between this cochain complex and the total cochain complex. And the formulas for the homotopy and the projection from the total complex to the cochain complex C are given by these formulas. And there is also like a symmetric version for columns. So if I have collection of modules regarded as cochain complexes concentrated in degrees 0 and homotopy retracts between them and each column of my double complex, I also have induced differentials between these modules given by this formula, and also some induced maps, which then give me the structure of a deformation or special deformation retract between this cochain complex and the total cochain complex of my double complex. And now we can use this theorem in the following application. We can use it to prove that the Deram cohomology of a smooth manifold is isomorphic to the check cohomology. So our double complex in this case is this one. So the rows are induced. The maps partial are just the exterior derivative on these between these sheaves of differential forms on open subsets of our good cover U, and the differentials delta are the differentials from the check cochain complex. And yeah, and then I will not really go into specific details of constructing these maps, but for this I recommend the book Differential Forms in Algebraic Topology by Tu and Bott. But essentially, for each row, no, for each column, I'm sorry. So for each column, we can consider the module of the differential L forms. And this map I is given just by restricting a given differential L form to the open subset in our cover U. And then the map P and the homotopy G can be constructed. And similar, so these would be like the omega L M, omega L plus 1 M, and so on. And also for the columns, I'm sorry, so for each row, we also have a deformation retract between the degree K check cochain module. So that would be DKU and so on. And this map J is induced by considering the constant sheaf on the real numbers included in the sheaf of smooth functions as the constant functions. And then the maps Q and H can be constructed. I will not go into details. But then by the double complex theorem, we know that this cochain complex deformation retracts onto the total cochain complex of our double complex. But also this vertical cochain complex deformation retracts onto the total cochain complex of our double complex. So by transitivity, this cochain complex deformation retracts onto this one, and so there is an equivalence on the corresponding homology groups, and the homology of this is the Deram cohomology, and the homology of this is the check cohomology, which gives us the isomorphism. Okay, and this concludes my talk. Thank you for your attention.
Are there some questions? Maybe I can start with one. So for the double complex that you showed, I didn't really understand where the complex, no, even before that, you had some arbitrary double complex, right? And then you had some, these C's. And so were these just some complexes where you find such a deformation retract, or were the C's kind of constructed out of the D's? This I didn't really understand.
Oh, so no, these C's are arbitrary. They just need to satisfy these like this relationship with the double complex, that there are these deformation retracts, but they are not obtained from the double complex.
Even though this is how you do it in case of the different forms. I mean, there you kind of start with the double complex, and then from this you get both of the single complexes, right?
Yeah, so in this example, definitely, but it doesn't have to be like this all the time.
Understand. Okay. More questions? Okay. Maybe from online audience, if you have a question, just unmute yourself. Okay, I think it was a very clear talk, so probably there are no questions. So let's thank Jakub again.
Thank you.
Now there's a short break and then we have the main seminar.